In my last video, I warned you about how complicated things get when you try to add a matrix attribute to your WebGL programs. I'm going to try to explain this today so that hopefully you understand what's going on and can add them to your own code as easily as any other kind of data. But first, I want you to help me with a little mystery. Here's a simple application. We won't be drawing anything here. We're just creating a WebGL program and then exploring it a little bit. Down at the bottom, I'm getting a list of all active attribute names and then looking up and displaying their location numbers. That's all. Very simple. Here at the top, I've got our vertex shader. It takes in some attributes, position, point size, color, and a model matrix. If you've not encountered matrices before, they're basically just a numeric array. And in this case, it's a 4x4 matrix that is used to describe a 3D transformation, which can include a variation of moving or rotating or scaling our primitives. You don't really need to understand how matrices work here or any of the math involved. You just need to know that it's a mat4, which again we usually visualize as a 4x4 grid of numbers. Anyway, those are our attributes, and as you can see, I've set their locations in the shader explicitly, like I usually do. And as you can see in the console, we're getting out those same original location values. Position is 0, point size is 1, and so on. I hope this all makes sense. If it doesn't, go back and watch my first video on attributes. But watch what happens when I let WebGL choose the attribute locations. First of all, it's chosen to put the matrix at the top of the list. And that's fine. It can do whatever it wants. But then it just ignores attribute locations 1, 2, and 3. So that's a bit weird, right? Well, let's put our position attribute back in at 0. Okay, that worked, and the matrix moved down to 1. But now 2, 3, and 4 are missing. Okay, well, let's add locations to our other non-matrix attributes. Oops, overlapping use of location. Yeah, that makes sense. And now we're back to working. I kind of prefer putting my fragment values at the end of the list, so move color down, and overlapping use of location. 0, 1, 2, 3. Okay, 4, 5, 6. Okay, 6. So, what an intriguing mystery. What could possibly be behind it? Yeah, okay. Mat4s always take up 4 attribute locations. That's the whole mystery. Sorry. So Mat4s take up 4 locations, Mat3s take up 3, Mat2s take up 2. This is a defined behavior of OpenGL and WebGL. Your applications will never compile if you allow your locations to overlap. But now you know, this kind of error is easy to spot and simple to fix. But this doesn't just mean you have to be careful about setting your locations. It also means that, for example, with a Mat4, it's basically been split up into 4 separate logical blocks across those locations. And that has a huge implication that can add a lot of bloat to your application. So when does this affect you? Basically, there are just 2 situations: when you are setting generic attributes and in instanced drawing. I suppose this first situation is probably a bit rare, or at least it's usually easy to avoid. Whenever you are using a generic attribute, you could also be using a uniform instead. They accomplish pretty much the same thing. There's a bit more to it than this, but they basically just set a shader value once for an entire draw call. But with uniforms, WebGL provides you with a custom function just for setting your matrix values, which is great. You'll use this a lot for view and perspective matrices, and maybe for lighting. So if you don't mind changing your shaders, you could just use a uniform and be finished in a single function call. If you can't do that, well, then you have to call vertex attrib 4f or vertex attrib 4fv 4 times to set a mat4 attribute. That would look like this. The first 4 rows of floats go in the attribute's location, the second goes into location plus 1, the third into location plus 2, and the last into location plus 3. You'll have to keep doing this anytime your matrix changes and before you issue your next draw call. So that's the first situation. The second situation is with instanced drawing, and this is a very common need for moving your instances in your 3D world space. Here you need to call vertex attrib pointer, vertex attrib divisor, and enable vertex attrib array for each row of your matrix. So that's 3 function calls, 2 times for a mat2, 3 times for a mat3, or 4 times for a mat4. If you use a vertex array object, you only need to do this once at initialization time, since VAOs preserve the result of all 3 of these function calls. I have an entire video on VAOs if you want to learn more about that. So for instance drawing, we'll have 1 or more buffers for holding all of our transform data that we'll need for our instances. And WebGL will need to know how to unravel this data, where to find each float or vec or matrix for each attribute. And for matrices, we have to call our vertex attrib functions 2 or 3 or 4 times. The first time we call vertex attrib pointer, it tells WebGL how to find the first 4 values of our matrix. The second call shows how to find the next 4 values. The third shows how to find the next 4 values. And the fourth shows how to find the last 4. And vertex attrib divisor and enable vertex attrib array just need to be called simply for each of the matrices' 4 locations. So if all of this slicing up of shader input seems overly verbose or intricate, you're right. I don't think it's too bad, but yeah, it does require a certain attention to detail. And although it's not really related, when we look at uniform blocks later in this series, you'll really get a sense of how much WebGL likes its data well organized. But it's a decent trade-off. A little extra work preparing our programs, and in return, we can be pretty much guaranteed that our programs will run faster and smoother. There are 2 last things that I have to say about matrices. I deliberately left these out because I honestly think they matter a lot less to new programmers than new programmers sometimes think. Shout at me in the comments if you think I'm wrong. That's fine. I usually am wrong, so no problem there. The first thing is that there's disagreement in the 3D world about how matrices are best laid out in memory. Some APIs, like DirectX, choose a method called row major, where matrix values are laid out like this. I don't have a horse in this race, but many have argued that this layout is very intuitive. OpenGL and WebGL choose a method called column major, where the numbers are laid out like this. All this really means practically is that if you're using WebGL, your matrix math library must produce arrays that reproduce this memory layout. If you want to write your own matrix math library, you have to produce arrays with this memory layout. That's it. Once you've done it, you're done. The only time this really becomes a major headache is if you're porting an application from an API that uses column major to another API that uses row major order, or vice versa. And if you're watching this video now in your career, hi, nice of you to drop by. But for the rest of us, it's not worth expending any mental energy on this. It's interesting, but it won't help you learn WebGL any faster. And the second thing is this video implies that there are only 3 matrix types that you can use in your shaders. For WebGL 2, that's actually not true. Here's the complete list. If you ever discover a need for any of these non-square matrix types and aren't sure how to write your JavaScript, it's just like with mipmap minification filter functions. Just pay attention to how the data type is named. If it starts with mat4, it takes up 4 attribute locations and requires 4 calls to each of our vertex attrib functions. If it starts with mat3, it takes 3 locations and 3 calls. And if it starts with mat2, it takes 2 locations and 2 calls. And after that, if you're still in doubt, just let WebGL choose its own attribute locations and see how it arranges things. That'll tell you everything that you need to know.